Hello students, welcome to the course on network theory. Today we are going to talk on two-port network, specifically the impedance parameters, which is otherwise called as Z-parameters. This topic is one of the most important foundations in electrical engineering because it helps us understand how complex electrical systems can be simplified into a manageable mathematical models. For example, in real engineering problems, we rarely analyze circuits component by component when the system becomes very large. Instead, we try to model their behavior using the parameter representations. In today's lecture, we will primarily focus on what is a two-port network, why we need to lead the two-port network parameters, how we try to perform the mathematical formulation, especially the Z parameters, the physical interruption of each parameter, reciprocity and symmetry conditions of Z parameters, real-world engineering applications where we try to use our Z parameters. So, by the end of this lecture, you should be able to understand the idea of simplifying the complex circuits and interrupt Z parameters equations conceptually, and also apply these ideas in circuit analysis problems. Let us begin our class. So, before we begin, we should understand that the mathematical formulation of the two-port network. Let us first understand why such theory is required in first place. So, let us start with a simple example. Imagine that you are given a practical engineering circuit, which may be consisting a large number of elements. The circuit may be consisting of a resistor, several voltage sources, it may be having current sources, or it may be having dependent sources, and it may be having complex interconnection between one small circuit to the other circuit. Now suppose someone asks you to determine certain performance quantities of this particular complex interconnection. So what you do? For example, they may be asked you to find the input impedance seen from the source. They may ask you to determine the voltage gain between 2 points. They may ask even to compute the current response under certain loading conditions. Each time such a question is asked, what would you like to do? You need to solve this circuit from the scratch. That is, you need to apply your mesh analysis or nodal analysis or any other circuit reduction techniques, and we need to perform the required thing. That is, whether you need to compute the input impedance or voltage gain, or how the current is getting response for a change in load, right? So what will you do? You write multiple equations, right, and solve simultaneous equations. So this becomes very complex as the circuit goes on increasing. So, and further, this process becomes increasingly time consuming. It also becomes mathematically heavy and sometimes unnecessary, especially if you are only interested in how the circuit behaves at its terminals. So this challenge led the engineers to develop a more efficient way of representing the circuit. So instead of focusing on the inter circuit, we focus on the external behavior of this particular circuit. So what we try to do, we try to abstract this complex circuit into a two-port network model, which try to behave as the original circuit. So in other words, we describe the circuit in terms of how voltage and current behaves at the point where it connected to the other systems. So for example, when we use a mobile phone, you do not need to know how the detailed semiconductor design inside the device. So what you will try to do, you will only care about how it responds to the input, such as the pressing buttons or sending signals, and what output it is trying to produce. Similarly, in engineering analysis, this large electrical circuit can often be represented as a black box. We do not always need to know every internal component. Instead, we try to describe the network using the relationship between the terminal voltage and the terminal current. These relationships are called as network parameters. So by determining a small set of parameters, that is the terminal voltages and terminal current, we can completely characterize the behavior of the complex circuit under different operating conditions. So this idea greatly simplifies the analysis and is widely used in circuit design, such as communication systems, power engineering, and control systems. Thus, the motivation of network parameters theory arises from the need to simplify the complex circuit analysis while retaining the accurate description of the terminal behavior here. The next question comes here is that what is a two-port network? So before actually going to the two-port network, let us understand what actually a port is. So a port is nothing but a pair of terminals. In electrical engineering, whenever we connect a circuit to the external world, energy must enter or leave the circuit, specifically connection between the points. These connection points are considered individuals but in place. So a port is defined as a pair of terminals through which electrical energy can enter or leave a network. This definition is very important, so let us understand it carefully. So why do we need a pair of terminals and not just a single terminal? The reason is that electrical energy transfer requires a complex path for current to flow. So if the current enters the circuit, it must have the path to return it. So this is consistent with respect to the Kirchhoff's current law. That is, sum of the incoming current should be equal to the sum of the outgoing current. That is, the charge cannot be accumulated at a particular node for an indefinite amount of time. Therefore, any meaningful electrical interaction between a network and the outside world must involve two terminals. So it means that whatever the current it is entering at one terminal, the same current should come away from this particular terminal. Then only this pair of terminals are called as a port. So at every port, we try to define two electrical quantities. First, we define the voltage across these two terminals. Second, we define the current flowing through this particular terminal. Because as and when the current enters this particular network, so as it's a closed path and the current is coming out of this, a voltage will be developed across these two terminals. So at every port, we try to define two quantities, that is the voltage across these two terminals. This voltage represents the potential that drives the current. And the second is we define the current flowing through the terminal, and this current represents the rate at which electrical charges move into the network and out of the network. Another important convention must be followed while defining the port. If current is assumed to enter at one terminal, then it is assumed that it leaves to the other terminal of the same port. This same convention ensures the consistency in mathematical modeling and helps avoid confusion during circuit analysis. Because of this, very port is always associated with two variables, one voltage and one current. This pair of variables completely describe how the network interacts with the external at the particular port. Now, you might wonder why this definition is so important in the context of today's lecture. The reason is that all the two-port parameters, including the Z-parameter, are built around these port variables, that is voltages across these terminals and the current entering this terminal and leaving this particular terminal. The reason is that instead of analyzing internal circuit components, we try to express the relationship between the port voltages and port current. Thus, a clear understanding of what a port is forms the foundation of all the network parameters. Now coming back to the actual question, what is a two-port network? So we have seen what is a port and port. So here the word called two-port. Nothing but we are going to have two ports. One port acts as an input and the other port acts as an output. Now, so in electrical engineering, we often deal with the circuit that interact with external world through specific connection points. Instead of studying every internal component, we focus on how the circuit behaves externally. So a two-port network is simplifying an electrical network has two distant ports for connection with external circuit. So this port might be connected to any other external circuit behind it, and this port is connected to the other one. For example, if you are having a complex network, what we are trying to do, we are trying to divide the complex circuit into a subnetworks. So these subnetworks connect to the other subnetwork in some way, either it may be series, parallel, or cascaded. Nothing but the input of some subnetwork is the output of this particular network can be the output of the other subnetwork. The output of this particular subnetwork will be the input to the other subnetwork. So we can say that at each port consists of two terminals, which means that the network has a whole of 4 terminals. These 2 terminals are typically referred to an input port, where the current is entering to this particular subnetwork, and this is considered the output port, where the output of this particular subnetwork is given to the input of the other subnetwork. So at the input port, we define a voltage and a current. Similarly, at the output port, we also define a voltage and a current. So in total, we are having 2 voltages and 2 currents that describe the electrical interaction of the network with the outside world. So we denote the input voltages as V1 and the input port current as I1. And similarly, we denote the output port voltage as V2 and the output port current as I2. Now, an important point to understand here is that these 4 variables are not independent of each other, because the network contains the internal elements such as resistors, inductors, capacitors, or active devices. The behavior of one port affects the behavior of the other port. So we say that these 4 terminals V1, I1, V2, I2 are not independent. They are dependent on each other. So these 4 terminals are algebraically written as A1 V1 plus A2 V2, V1 I1 plus V2 I2 plus C1 equal to 0, and A3 V1 plus A4 V2 plus B3 I1 plus B4 I2 plus C2 equal to 0 in this particular way. And here C1 and C2 is generally represented as the assuming that we are having a circuit that has dependent sources. If the dependent sources are not present, that is, if you assume the network total two-port network is a linear circuit, in the absence of dependent sources, then C1 and C2 becomes 0. So this interdependence of these parameters is what makes the two-port analysis both interesting and useful. So two-port networks are extremely common in practical engineering. For example, if you try to consider an amplifier. An amplifier receives a signal at its input port and delivers an amplified signal at its output port. Instead of analyzing every transistor and resistor inside the amplifier, what we try to do, we can represent it as a two-port network and study only the terminal behavior. Similarly, the filters used in the communication systems can be treated as the two-port networks. They accept signals at one end and they provide the filter signals at the other port. So another important is the transmission line. In power systems and communication systems, transmission line connects the sources with the loads. So the input port where the power is getting transmitted and the output port where the power is getting delivered or received. So these lines can be represented as a two-port parameter for easy analysis. Thus, the concept of two-port network allows the engineers to simply analyze the complex circuits into manageable models. Now, this naturally leads to an important question. If a network has 2 voltages and 2 currents, how exactly are these 4 variables related? This question is crucial because understanding this relationship allows us to predict the network behavior under different operating conditions. To answer this question, engineers have developed various parameters. For example, we are having 4 elements here, out of which we need to make the input current and the output current coming out of this terminal should be equal. So this can be possible only in the 2 ways. Either connect the 2 terminal device over here and 2 terminal device over here. So the current enters this particular resistor, comes out of this, and the current entering this particular resistor and any other 2 terminal element comes away from this. But there is no interaction between the input and output port. So if we useless. So it does not make any sense. So these two input networks are interconnected in some way. So if you are trying to send a current I1 here, the sum of the current of I1 might be leaving this particular port or terminal, and the other current might be leaving in this particular terminal. So what we need to make is that these two terminals act as a port. What the condition? The input the current entering this terminal should have the same amount of current leaving this particular terminal. So in order to do that, what we are trying to do, either we add an external source externally, that is, it may be a voltage source or a current source. So if you are trying to add a voltage source here, as it becomes a closed path, the current amount of current entering here will be the same amount of current coming out of this terminal. And we can even add a current source. So the amount of current entering this particular terminal will be the same amount of current coming out of this particular terminal in order to satisfy our Kirchhoff's current law. Thus, so out of these four parameters, four elements, that is V1, V2, I1, I2, two will be known and two are unknown. So the number of combinations here we are getting is 4C2. So 4 factorial by 2 factorial and 2 factorial. Nothing but we are going to have 6. So we engineers have developed the parameters, 6 different parameter models, such as it may be your impedance parameter, admittance parameters, hybrid parameters, inverse hybrid parameters, transmission parameters, and the inverse transmission parameters. In today's lecture, we will primarily focus on the impedance parameter model, also known as Z-parameter model. This model provides a systematic way to express the relationship between the port voltages and currents. Now, students, we have come to the heart of the lecture, which is the mathematical model of our impedance parameter. Up to this point, we have discussed what is a two-port network and why we need this particular parameter representation. Now, we are going to formally express the relationship between the voltages and currents in such a network. The fundamental idea behind this Z parameter is that the voltages at the ports are expressed in terms of the current at the particular place. In other words, the port voltages are treated as a dependent variables and the port currents are treated as an independent variables. This leads to the following mathematical relationship. The voltage at port 1 V1 can be written as Z11 I1 plus Z12 I2. Similarly, the voltage at the port 2 can be denoted as Z21 I1 plus Z22 I2. So let us pause here and understand the meaning of this particular expression. This equation actually tells us that voltage at a particular port not only depends on the current entering at that particular port, but also it depends upon the port current that is entering the other port. So this is because electrical networks are interconnected systems and energy can be transmitted internally from one port to the other port. Thus, the behavior of one port influences the behavior of the other port. Now, instead of writing these two equations separately, we can write them in a more compact and elegant matrix form, which is written over here. We write voltage vectors V1 and V2 in a column vector and I1 and I2, which are common to both these equations, as another column vector. Between them, we place a matrix containing the four parameters, that is Z11, Z12, Z21 and Z22. So, this matrix representation is extremely powerful because it allows the systematic analysis of the networks, especially when we are trying to deal with the larger systems. In advanced electrical engineering subjects, like matrix formulation becomes very common. So, this is an important point in building the mathematical maturity as an engineer. Now, let us discuss what these four constants actually represents. So, this contains Z11, Z12, Z21 and Z22. These define the electrical behavior of the network. They capture how voltages and current responds at the terminals. So they are called the impedance parameter because each term has units of the impedance. So they are called impedance parameters because each term has the units of impedance. that is voltage per ampere. If Z12 is the voltage V1 divided by current I2. So even the transfer parameters such as Z12 and Z21 have impedance units because they relate voltages at one port and the current at the other port. So we will be trying to discuss the transfer impedance in the in the coming time. Okay. So another important point to understand is that these parameters depend only on the internal structure of the network. So when we are trying to divide a complex network into a subnetwork, so this particular matrix or parameter represent the internal structure of that particular subnetwork. So they do not depend how the network is connected externally. Then it may be connected in series, parallel, cascaded, or any other ways. This means that whether you connect a load, a source, or another circuit to the port, this Z parameter does not change. This property makes the parameter model extremely very useful. So once we try to determine these Z parameters of the network, we can use them in many different analyses. So we try to develop an equivalent network, and this equivalent network try to behave as similar to the actual subnetwork. So in engineering terms, it means that network can now be treated as this particular black box whose behavior is fully described the network parameters, that is Z11, Z12, Z21 and Z22. So this greatly simplifies the analysis, especially when multiple stages of circuits are connected together. So now let us understand how these parameters, that is Z11, Z12, Z21 and Z22 are actually computed. So we have seen in the previous slide that we have written the two equations, that is V1 is equal to Z11 I1 plus Z12 I2. So V2 is equal to Z21 I1 plus Z22 I2. So our objective here is to identify these parameters Z11, Z12, Z21 and Z22. So how do we find this Z11? Is that we try to make this particular term Z12 I2 as 0. So if we try to make this particular term equal to 0, so our equation becomes V1 equal to Z11 I1. So my Z11 can be given as the ratio of V1 by I1. So we are saying that we are trying to open the second port, so which is written in this particular way. So we are having a two-port network, and this is a black box. This is a black box where we don't know how the circuit is connected in this, but we are assuming that the circuit is a linear circuit, and we are having the absence of any dependent sources in this particular subnetwork. So as I said, we are having V1 I1 and V2 I2, and we say that the voltages, the terminal voltages V1 and V2 are depending upon the I1 and I2 current, right? So as I1 is became an independent term and V1 and V2 became a dependent term, so we are connecting a current source here I1, and we are having a I2 current. But as I said, in order to find the parameters Z11 and Z21, we are trying to make this particular I2 as 0. Nothing but we are trying to eliminate this particular term. As we cannot make Z12 equal to 0, the only option which we are having is I2, which is a dependent term, independent term, which we have control over it. So by making that I2 equal to 0, these two terms becomes 0. As a result, we will be able to compute Z11 and Z21. So we are trying to leave the port 2 completely unconnected, that is, we are trying to open such a circuit. So this physically forces the output current to I2 equal to 0. So we try to find the I1 current which is pushing inside the particular port 1. So once we try to measure this I1, and if we try to measure V1 and V2, that is voltage across these two terminals and voltage across these two terminals, we will be able to compute Z11 and Z22. Similarly, in order to compute Z12 and Z22, what should we make? We need to make this particular term Z11I1 and Z21I1 as 0. However, if you observe carefully, then this Z11 and Z21 cannot be made 0. So we are trying to force this I1 equal to 0. As a result, we will be able to have ZV1 equal to Z12I1, sorry, Z12I2, and V2 equal to Z22I2. So as a result, we are going to have Z12 equal to V1 by I2 and Z22 equal to V2 by I2. So when this happens, whenever my input port, that is I1, equal to 0, that is we are trying to open the input port. This is how we try to get the parameters Z11, Z12, Z21 and Z22. Okay. Now let us see the names given to this particular parameters, that is Z11, Z22, Z21 and Z12. Okay. So when we are trying to compute our Z11, we are trying to make my I2 port equal to 0. So we are calling that it is an open circuit. We are trying to have it as an open circuit. And what we are trying to do? We are trying to drive, we are supplying the input current source, and we are trying to measure the voltage at the same point. So we are going to call it as a driving point, open circuit driving point, where we are trying to measure, we are trying to connect I1 source, and we are trying to measure the voltage at the same terminal. So we are going to get, we are going to say at the driving point input impedance. Why impedance? Because it's a ratio of voltage and current. So the name for this particular Z11 can be given as open circuit driving point input impedance. What about this Z21? This is also obtained when we are trying to open the second port. So it's an open circuit, and we are trying to put an input at I1, and we are trying to measure voltage at the other output terminal. So it's a transfer. And we are going from 1 to 2. So it is a forward transfer, and it's a ratio of voltage to current. It is a impedance. Similarly, the Z22, it is also obtained while we try to open the input terminal. So it is an open circuit. We are trying to connect the I2 source at the second port, and we are trying to measure the voltage at the same terminals, output port. So we are going to say it's a driving point, and to represent here output. So it's a output impedance, because it's a ratio of voltage to current. Similarly, the Z12, it can be said at open circuit transfer, but we are trying to give an input at the second port, and we are getting the we are measuring the voltage at the first port. So it's a reverse. So we can write open circuit reverse transfer impedance. So here the word generally transfer represent a simple meaning that measuring an effect across two physical different ports. Now suppose you create some disturbance in room number 1. That is, for example, you are trying to play a loud music in room number 1. If the wall between the rooms, say room 1 and room 2, is very thick and very insulated, then only very little sound reaches the room 2. But if the wall is thin and has openings, then the sound will always easily travel from room 1 to room 2. This idea of disturbance is transferring help us understanding the transfer impedance. So let us now map this analogy to the electrical parameters. The parameters Z11 represent the impedance seen at the port 1. In our analogy, this is similar to how your resistance or opposition of the current exists within the room 1 itself. Similarly, the Z22 represents the impedance seen at the port 2, where this is analogous how your resistance exists within the same room 2. Now, the more important parameters, interesting parameters here is the Z21 and Z12. So, the parameter Z12 represent how much voltage appears at port 1 when the current is applied at port 2. In the room analogy, this is like how much disturbance in room 2 affects room 1. Similarly, the Z21 represent how much voltage appears across the port 2 when the current is applied at port 1. This is like how much disturbance in room 1 affects the room 2. So, these two parameters essentially measure the interactions between the two ports. If the coupling between the two ports is strong, then the transfer impedance, that is Z12 and Z21, will be having very large values. This means that the activity at port 1 significantly affects the other port. If the coupling is very weak, then this transfer impedance will be very small. This means that the two port behaves almost independently. This idea is very important in practical circuit design. For example, in amplifier design, sometimes we want to use the strong coupling to transfer signals effectively. But in other situations such as noise oscillations or filter design, we may want weak coupling. Thus, understanding the physical meaning of Z parameters helps engineers make design decisions, not just perform the calculation. So, whenever you see the Z parameter equations, do not think of them as an abstract symbol. Instead, we need to think of them as describing how energy or signal is transferring occurs inside the network. This physical interpretation makes the mathematical model very meaningful and easier to apply in real engineering problems. So, now let us recapitulate the impedance parameters. Here we are writing Z11. This 11 is mainly given as we are trying to apply with the excitation at port 1 and we are trying to see the response, that is at port 1 itself. The response is the voltage V1 and the excitation is I1. So, it's a 1-1 ratio. Here we are having 1-2 because we are trying to apply at the port 2 and we are trying to see the response at port 1. Similarly, we are trying to apply the excitation at port 1 and we are trying to see the response at port 2. Here we are trying to see the excitation at the same port. We are trying to excite and see the response at the same port. That is the reason we are going to call this is a driving point 1-1 and 2-2, and 1-2 and 2-1 are called the transfer impedances. Okay. Right. So this is an equivalent circuit which tries to replace the black box. So after finding the Z parameters, that is Z11, Z12, Z21 and Z22, we try to predict how my equivalent circuit will be, right? So in previously we assumed that this particular box is an unknown, it's a black box. We don't know how the circuit is connected. Now after obtaining the parameters Z11, Z21, Z22 and Z21, so we are able to construct, we will be able to construct how the actually this circuit can be, which tries to behave as the original one. So we are having two equations. Here we are having V11 so we are having V11 V1 equal to Z11 I1 plus Z12 I2. So if you are trying to see here, the voltage is getting divided into two parts. So if we are trying to apply our Kirchhoff voltage law. So if you are trying to assume we are having a V1 input, so we are going to have two voltage drops. That is here at this particular point and another particular point. So this, but as we are trying to have I1 current flowing through it, so this one we generally call as Z11. So one of the voltage drop occurred here is Z11 I1, and another is the I2. Here we are having I2 is the current which is representing the current at the port 2, and as it's relating to the port 1, we'll try to make use of the dependent sources. As we require this is a voltage, then we try to use dependent voltage source, but this parameter is depending upon the current, so we try to make use of current dependent voltage source. At what magnitude it is having? It is Z12 I2. So V1 will be equal to Z11 I1 plus Z12 I2. Similarly, here we try to represent the second equation, V2 equal to Z21 I1 plus Z22 I2. So this whenever we apply the having voltage V2 source here, the current flow through this element. As a result, we are going to have a voltage drop of Z22 I2, and we are having another term, this is I1. Yet this is at port 1, the current at port 1, which is relating to the voltage at port 2. So we need to have a dependent source. So what kind of dependent source we need to take? It is Z21 I1. It's a product of impedance and current. That is, we need to take a voltage dependent source or dependent voltage source. And to which what kind of dependent voltage source? We are depending upon the current. So we are trying to choose the current dependent voltage source here. So how they are connected? They are connected in series, because here V2 is getting distributed among Z21 I1 and Z22 I2. So this is the interconnection of or equivalent circuit of our Z parameters. So we can replace this black box with the which is an actual one by this equivalent circuit model. This model actually mimics the original complex circuit exactly by using our Kirchhoff's voltage law. Now students, let us discuss another important terminology in this particular thing, that is the condition for reciprocity. Here a two-port network is said to be a reciprocal if the transfer impedance from port 1 to port 2 is equal to the transfer impedance from port 2 to port 1. That is, whenever my Z12 is equal to Z21. Mathematically, this is equal to as Z12 equal to Z21. At first glance, this may look like a simple quantity, but physically it represents a very meaningful engineering concept. Reciprocity here means that the influence of one port on the other are mutually equal. So nothing but the amount of influence of port 1 and on port 2 and the influence of port 2 on port 1 are equal. In simple words, if the current applied at port 1 produces a certain voltage response at port 2, and applying the same current at port 2 should produce the same voltage response at port 1. Nothing but the ratio of the excitation to the response is equal. This indicates that the network behaves identical in both directions of the signal transfer. Let us understand this using an intuitive example. Consider a pure resistor network composed of only resistors. If you inject a current at one end and observe the voltage at the other end, you will get a certain response. Now, if you reverse the experiment, that injecting a current at the second terminal, second output port, then observe the voltage at the first port, you will get the same response. This means that because we are having a passive element which are linear network, they obey the reciprocity principle. However, this is not always true for all the electrical networks. For example, transistor amplifier circuit are generally non-reciprocal. This is because of presence of active components, nothing but the dependent components, like your transistors introduce a directional behavior. They are designed to amplify the signal in one direction, not equally in both the direction. Similarly, controlled sources are also break the reciprocity. Another important example is the communication systems. In transmission line, without active elements, reciprocity holds. But when amplifier or isolators are introduced, reciprocity may not hold. From a design perspective, reciprocity simplifies analysis because it reduces the number of independent parameters which we need to determine. For example, under normal conditions, we need to measure the 4 parameters, that is Z11, Z22, Z21 and Z12. As Z12 is equal to Z21, we need to compute only the 3 parameters, that is Z11, Z22 or either of Z12 and Z22. So now summarizing this concept of reciprocity, it means that a network is reciprocal only if my Z12 is equal to Z21. This means that signal transfer characteristics are identical in both directions. So reciprocity is generally observed in passive linear network, and it may not be true or violated when we have the active networks. Now we have another condition called symmetrical condition. So let us discuss another property of this. So a two-port network is said to be symmetrical if the input impedance is equal to the output impedance. That is, impedance Z-net from the first port is equal to the impedance seen from the second port. Mathematically, Z11 equal to Z22. At first glance, this may look just as a simple equality, but physically it has very deep meaning. It means that if we interchange the input and output terminals of the network, the electrical behavior of the network exactly remains the same. In other words, the network does not prefer one side over the other. Let us try to understand this with a practical intuition. Imagine you have a circuit placed between 2 points in a system. Now suppose you remove the source from the left and connect the same source to the right. If the network is symmetrical, you will observe the same impedance value. This indicates that the internal structure of the network is always balanced. Now consider a simple example. A transmission line segmented that is uniform throughout its length behaves approximately like a symmetrical two-port network. This is because the electrical properties are the same when viewed from either the input port or the output port. Similarly, many passive filter sections are designed to be symmetrical so that signal behavior remains consistent regardless of the direction. This becomes very important in communication systems where signal may be travel in both the directions. On the other hand, we consider an amplifier circuit. Your amplifier circuit is not a symmetrical because it tries to send the signal in one direction. So if you look at the input terminals, you see a certain impedance designed for the signal reception. But if you see the from the output terminal, the impedance is usually very different because it is designed to deliver the power at the load. Therefore, most active circuits are asymmetrical. Symmetry is therefore mostly a feature of passive and balanced network structures. So from a design perspective, the symmetrical networks are easy to analyze and often provide predictable performance. So to summarize this concept, a two-port network is a network is a symmetrical if my input impedance is equal to the output impedance, that is Z11 is equal to Z22. This means that the input and output characters are identical. Such networks are commonly found in filters, transmission systems, and matching networks.